In today's tutorial we will try to solve a mechanistic riddle starting from Wagner-Meerwein. Under acidic catalysis, water is eliminated and astonishingly camphor will be the product of this transformation. So not only is water eliminated, but some kind of rearrangement had taken place. So, first step of the reaction, protonation will take place where we have high electron density free electron pairs like those at the hydroxyl oxygen. So, protonation of the oxygen will lead to a nice water-leaving group. If it leaves then the molecule, such a secondary carbocation will remain. This wants to be stabilized. One possibility is by deprotonation to get to a charge neutral molecule, this one. So deprotonation at that CH2 group here will lead to this side product. But with this side product we are still far away from our target molecule. No problem, since this is an equilibrium reaction. We can reprotonate, getting again to this secondary carbocation and being again on the reaction pathway towards the target molecule. Well, second way to stabilize such a secondary carbocation is the migration of a carbon-centered group and forming a tertiary carbocation, which is thermodynamically more stable compared to a secondary one. So let's assume that this CH3 group migrates to this position, taking this electron pair with it. Well, then we would get to this reactive intermediate, the carbocation at the bridgehead position. However, this reaction step is just not possible, because then this CH3 groups should move somehow upwards and getting to this position from that side. This is not possible. Such a Wagner-Meerwein rearrangement has to be prepared by a suitable orbital interaction. Therefore, I have drawn the orbitals which are involved in this structure. So, at this sp2 hybridized center, we have an empty p orbital, this one here, and as we see that CH3 group is in front, and this CC bond here is perpendicular located towards that empty p orbital. Perpendicular means no interaction, no overlap, no interaction. But here for this CC bond, we formally have the overlap of two sp3 hybrid orbitals, and those are in line with that empty p orbital. Therefore, electron density of this can interact also with the p orbital, if the electron density migrates from here to that means from here to there a bond is formed, a CC bond is formed, while at the same time the bond between that carbon and that carbon is broken. So this CH2 group migrates within a Wagner-Meerwein rearrangement. And what will be the result? Let us draw this structure once again and then introducing the changes which occur here. As we said, this carbon migrates to this position and takes those electrons with it. So then this bond is formed, positive charge is gone here, but develops at that carbon. So, but in this structure here, the bond angles are somehow distorted. Let us draw it, correct it. Here we will have an sp2 hybridized center, and here from sp2 it has been transformed to sp3, so a tetrahedral carbon here. Well, let's draw that a little bit different. Well, here we have the carbocationic center. We have here that CH3 group sitting at that positively charged center. For getting to a neutral, charge-neutral molecule, we will simply deprotonate. Let's draw that then. This bond is in front, and if we compare this structure with that, it's just another perspective. We just have to rotate that by 120 degrees, then this exomethylene group, this one, will end up here. So this is essentially the same molecule. And by that we have completely pictured that reaction pathway from Isoborneol to camphor. Thanks for listening.